A statement from Durham School lecturer Carlos stated, "I have dedicated my life to promoting a particular theory about the universe. Then this occurs. Attention is being paid to the conjecture. I welcome this exam since it is through investigation that science progresses and gains momentum." In essence, the James Webb Space Telescope is challenging several long-held cosmological beliefs that have been accepted as true for a century. It has been demonstrated by another ultra-tracked-down image that we have made blunders in space research. The telescope is somewhat problematic. It was designed to reveal the universe's main stars. The previous point of view could present an entirely new and valid viewpoint. While some scientists are disappointed by these new revelations, others applaud the progress made, as it has long been clear that our earlier hypotheses were flawed. The anomalies in determining the universe's rate of evolution alone ought to have prompted concern. In any event, academics a startlingly long time ago stuck to antiquated conjecture rather than precisely decoding these warnings. The universe's oldest light, known as the cosmic microwave background radiation, CMBR, was created about 380,000 years after the Big Bang, when the universe had cooled down sufficiently for protons and electrons to combine to form stable hydrogen particles. Reionization, a result of this alteration, gave rise to the universe's transparency to light. American scientists Arnold Penzias and Robert Wilson discovered the CMB for the first time in 1964 while developing new radio receiver technology. They heard a continuous sound overhead coming from all directions. At first, the Big Bang theory was thought to be strongly supported by this discovery. Wilson and Penzias shared the Nobel Prize, and their discoveries served as a significant precursor to later developments in space science. Microwave background radiation, CMB, likely sheds light on the early cosmos, and minuscule temperature variations provide crucial information about the circumstances immediately following the Big Bang. Scientists estimate important aspects of the material universe, such as the rate of expansion of the universe, using the CMB as a reliable marker. In the late 1920s, Edwin Hubble had previously made such evaluations. He observed that galaxies far away from us were traveling in all directions, and that there was a speed-to-distance relationship between them. This relationship is now known as the Hubble law or the Hubble constant. Even though Hubble's calculations were not as accurate as they are now, they were crucial in the discovery of the CMB. After recalculating the expansion rate, experts discovered that it was much less than Hubble's original projection. The inconsistencies in the expansion rate estimates have been known since the 1990s. However, more precise estimates were obtained by recalculating the data using Type I supernovae as standard candles. Experts have conjectured that there may be problems with the theory of universal expansion or the CMB data processing techniques. This divergence, also referred to as the Hubble strain or S8 tension, raises the possibility that there are serious problems with our current understanding of the cosmos. The James Webb Space Telescope, JWST, has produced amazing data since it began operations, which may help to clarify the problem. Ancient and developed worlds, potentially formed prior to the Big Bang, are putting long-held scientific beliefs to the test. The rate of universe expansion and the notion of how things came to be are under severe investigation, which is regarded as the biggest challenge facing astronomy today. Recent photos show a universe that is very different from earlier models. The S8 tension has acted as a precursor to the awareness that our knowledge of the cosmos might be imperfect, causing researchers who continue to adhere to antiquated theories to struggle. Many investigators are puzzled and frustrated by this uncertainty. We need to comprehend how science operates in order to handle this situation. To reach their results, hypothetical scientists combine observable data, mathematical models, and logical reasoning. They learn via speculative analysis, test findings, and oddities they observe. By itself, the word theory suggests concepts and creations rather than absolute truths. Our rational understanding is derived from data obtained from neutrino and gravitational wave detectors, images provided by telescopes, and sound waves and radiation acquired by radio telescopes. We can now investigate the oldest light in unprecedented detail by dissecting it into its various frequencies thanks to the James Webb Space Telescope. It is able to display the elements, mass, and number of stars that were present in galaxies billions of years ago. But Webb's photos might have certain drawbacks. For example, because of gravitational lensing, it might be difficult to discern between galaxies and black holes that emit light that is similar in intensity. Our knowledge has grown to accept different scenarios as bits of the whole, frequently discounting competing theories. Important hints provided by recent James Webb Telescope discoveries may enable the replacement of antiquated hypotheses with more insightful ones. These findings seem so remarkable that scientists are currently having difficulty coming up with new interpretations. Many specialists are concerned about the recent discoveries, which are upending the fundamentals of physics. Today's physics is still heavily impacted by the discoveries made by Isaac Newton in the 17th century. His equations of motion and gravity have served as the cornerstone for our knowledge of the physical cosmos for millennia. On Earth, Newton's laws operate flawlessly under normal circumstances. But, in space, they needed to be expanded, a task primarily completed by Albert Einstein in the 20th century. Published in 1905, Einstein's special theory of relativity altered our perception of reality by demonstrating that the laws of physics are dependent on the velocity of the observer. With the publication of his general theory of relativity in 1915, he expanded on these concepts by using mathematics to anticipate gravitational anomalies resulting from space-time curvature brought on by massive objects like galaxies or stars. Although many aspects of Einstein's theories were evident, he was aware of their limits and attempted, but was unable, to develop a cohesive framework. This is an undertaking that no scientist has yet succeeded in. Trying to figure out where the mistakes might be is fascinating. Renowned American astrophysicist Michio Kaku suggested that a Nobel Prize might be awarded for addressing this puzzle. We need to investigate whether reality has been misconstrued, whether anomalies have been misinterpreted, or whether there may be a problem with the telescopes themselves. In the cosmic crisis, dark energy and dark matter are the main suspects. Although neither dark matter nor dark energy have been explicitly seen or demonstrated to exist, current models indicate that they jointly account for roughly 95% of the universe. They might not even exist, or they might have characteristics that are still unknown to us. The idea that the characteristics of dark matter have changed over time and may now exhibit intelligence is one that is currently under discussion. The expected behavior of gravity, which is to generate attraction through mass or space-time curvature, has not been conclusively shown. Even though Einstein's theories regarding space-time curvature have been confirmed numerous times, it is still possible that gravity has unanticipated characteristics or that gravitational pull is being caused by some other phenomenon. In cosmology and space research, some traits have been recognized as basic constants across time, and their constancy has helped to prove their reliability. Small differences in these constants, according to calculations, may provide new information about the universe and maybe explain events that do not require dark energy. It's also feasible that inaccurate distance measurements and galaxy ages have resulted from our misinterpretation of light shifts. It's possible that we misinterpreted the cosmic microwave background radiation, or that our assumptions about the properties of the cosmos were incorrect. It's possible that the Big Bang Theory is challenged by the possibility that the cosmos doesn't have a single point of origin. It is impossible to completely rule out tiny flaws in the Webb telescope or other observational tools. Scientists and experts agree that errors can always occur in data management, equipment, or interpretation. Cosmological ideas are constantly being re-evaluated, which emphasizes the fundamental aspect of scientific advancement, the capacity to modify and enhance our comprehension in response to fresh data. The discoveries made by the James Webb Space Telescope mark a critical turning point in our quest to understand the secrets of the cosmos, not just a leap forward in technology. It is crucial to understand the larger context and ramifications of such rational changes in the field of cosmology as we grapple with these insights. The process is frequently motivated by the need to adjust theories in light of fresh information. Although the finding of odd anomalies or contradictions in accepted ideas might be disturbing, it also offers a significant chance for scientific advancement. In cosmology, theoretical models are created to offer a precise framework for comprehending the universe's beginnings, growth, and evolution. But these models need to be tested and, if needed, updated to account for fresh information as it becomes available. The nature of dark matter and dark energy, which are crucial to modern cosmological theories, is one main topic of study. It has been suggested that differences between the mass anticipated by visible matter alone and observed galaxy rotations can be explained by dark matter, an invisible kind of matter that neither emits nor absorbs light. In a similar vein, the apparent faster expansion of the cosmos was explained by the introduction of dark energy. Nevertheless, dark matter and dark energy continue to be mysterious while playing crucial roles in current models. Earthly studies have not been able to unambiguously discover them to date. This has prompted scientists to investigate many theories and plausible justifications. A further obstacle to comprehending dark matter and dark energy is the enormous breadth of cosmological research. While indirect evidence for these components can be found in observations of far-off galaxies, the cosmic microwave background radiation, and other large-scale events, their precise composition is yet unknown. Scientists have been considering a variety of possibilities as a result of this ambiguity, ranging from changes to current models to completely new principles. Certain theories propose that dark energy might be a new fundamental force, or that dark matter might consist of more exotic particles than previously believed. The study of cosmic inflation is another fascinating field of cosmological research. According to this view, the large-scale structure we see now originated from the universe's early fast expansion. Although the universe's homogeneity and flatness have been satisfactorily described by inflationary theory, the theory also begs the question of what the inflationary phase was like. Our understanding of the early history of the universe may need to be updated in light of observations that contradict well-established models of inflation. And last, the pursuit of extraterrestrial life continues to be a motivating factor. In the study of space, finding exoplanets, or planets around stars outside of our solar system, has created new research opportunities for the study of the circumstances required for life. Modern telescopes, like the James Webb Space Telescope, allow us to examine these exoplanets' atmospheres in search of possible biomarker traces. Our knowledge of the universe and our place in it is significantly affected by the prospect of life beyond Earth. In conclusion, the scientific method's tenacity is demonstrated by the reassessment of cosmological theories in light of fresh data. Scientists are revisiting and improving long-held beliefs as a result of the amazing insights into the universe that the James Webb Space Telescope and other cutting-edge observation tools have provided. In order to advance our knowledge of the cosmos and tackle the central issues of cosmology and space science, this ongoing process of investigation and revision is vital. We are still searching for answers to important problems as we continue to explore the universe, and we hope that our efforts will encourage future generations to go beyond what is thought possible.